Great. Right, I have to start with a small confession. I last spoke in the States 5 years ago. I think it was in Chicago. And I said something I felt very honestly at the end of that talk. I said that here in the US, you were 20 years behind Europe. Now, I have to say that, in terms of mass timber, now I have to say that, no, but to be honest, everything I've seen in the past 2 days, I genuinely think that you've caught up. And in fact, the developments you're seeing in sort of the, developments in the IBC, I really think within a couple of years you are actually going to be ahead of Europe in this game. So it's actually, it's pretty impressive, I have to say. This is a collection of the tallest wood buildings which have been built across the world in the past 10 years. And I think you can see that something pretty radical is happening. And so I wanted to ask, why is this changing? And what is the future for wood? I lead a team of timber specialists back in London. We are, in terms of Europe, we are writing a load of the stuff behind the European codes, which is enabling a lot of these bigger buildings. So I want to give you my vision of where wood is going to be in 10 years' time. Now, I thought I'd start with a picture of home. This is not too far from where I live, but this is a very important building. This is probably the oldest wooden building in Europe. You can see the wooden wall. That was built just before the French invasion. So this is nearly 1,000 years old. So I think anybody who suggests wood can't last, keep it dry. That is the trick. Fungus needs water to survive. It's like any organism like us. So overhanging roof, lifted off the ground. And that's, I think when we use wood in our new structures, that is really important. The wooden structure should not see the rain. Now, I think the real challenge with wood is it grows in these very awkward shapes and sizes. These trees, they are tapering. So if you're going to use those efficiently, without having huge amounts of wastage on the sides, you're going to cut those into fairly short lengths. That was fine when we were building small medieval barns. But, come the 1850s, we wanted to build the airports of the day, which were, of course, the big railway stations. This is King's Cross. This is, in fact, a photograph of platform 9 3/4. Have a look on the left. On the left is the original drawing of that roof. You can see that in fact the cast iron shoe is still in place, but the original arch members were actually made of wood. Those were short, as I say, cut from those trees, short lengths of wood, bolted together to make wooden arches. Now, I think you can imagine that just bolting bits of wood together is pretty weak. The strongest way to join wood, of course, is to glue it. And for that, we had to wait for the Second World War. During the war, waterproof wood glues were developed. And I show you the Mosquito because that was one of the very first uses of those new waterproof glues. Obviously, if you were going to fly through the clouds, you really needed something that was waterproof. Look on the left, that's the detail of the wing, and what you can see is a tiny little glulam beam. So now we've got decent glues. We can take those short lengths of wood cut from the tree. We can join them end on end using one of these we call a finger joint, nice long length of glue line loaded in shear. We can take that long plank, we can pass it through a glue curtain. What you've got is you've got resin and hardener, so the resin and the hardener gets mixed on the surface of the wood, clamp that together overnight, and we can make really large pieces. Now, but there's another reason that we use, or we make glulam beams, which not many people realize. And that, of course, is that, wood is a natural material, but what that means is it's incredibly variable in its strength. It has knots, the remains of the branches, and you can imagine if those knots are in the wrong places, they can massively pull down the strength of the member. Now, in engineering, we want confidence about the strength. And there is this amazing thing whereby if we take a log, chop it up randomly, and then glue those bits back together again, those knots, those holes, don't go all the way through, and so we end up with something which is much stronger and more predictable in its strength. So that's the great beauty of engineered timber. glulam beams, really, which is you can make much larger members and you can make stronger members. And this is the largest glulam beam I've ever seen. Just for sense of scale, it's compared against one of our graduate engineers. That's Jane, who actually did the engineering for the Aquatic Centre in London. And when we took this, we were actually looking to try and use wood for the roof of the Aquatic Centre. We didn't in the end. Now, of course, wood has always been a massive part of the construction market, but it's very much been for these sort of light frame buildings. Michael Mark showed this same photograph yesterday. These are great. American invention, 1830s. There's a guy called Charles Snow. He says, let's not do all this labor-intensive mortise and tenon joints. We need to build houses really quickly and cheaply. Why don't we just take some little bits of wood and fix them together with these new machine-made nails? And he came up with this really strange phrase. He said, it's as easy as blowing up a balloon. And to this day, these are referred to as balloon frames. But I think that sense in which wood is really easy to build with is something that's really important to remember, because that applies to modern timber construction today as well. Now, I think the big change that we've seen, and you all know this, is that we're seeing much bigger structures now made out of wood. And so the question is, why is that? Yes, wood is renewable, but I don't have any clients who will pay more for a renewable and more sustainable building. So there have to be other reasons. And I think there are two reasons. The first is this. Now, this is a photograph I took 13 years ago. When I took this, this was one of the very few bits of CNC fabrication in the structural timber industry. Now just about every factory has one. And we've already heard that with CNC you can machine wood down to a 1/16 of an inch or even better. So think about precast concrete, you're probably only at about 1/2 inch. So really high tolerances. That was the particular building that we built with that, but 459 different pieces. How could you have done that economically in any material other than wood using CNC fabrication? And obviously the other big wood innovation is CLT. And this, it was only invented in 1998. It has only been cheaply available for about 5 years. So if you combine CNC with CLT, your wooden building becomes like a giant piece of flat-packed furniture. So this is a 120-foot long sculpture which we built in London. The entire thing took 7 days to erect. So CNC, high tolerances, large bits of CLT. So what wood gives you, it gives you speed. And so it fits in so well with this whole drive for prefabrication. Now this, of course, the sort of real breakthrough building worldwide. War Thistleton working with Technica engineers. And this was a breakthrough for two reasons. First of all, it was really that first sort of tall wood building, that sort of tall wood building worldwide. But the other breakthrough was this was wood as a great building material. You cannot see the wood in this building, but it doesn't matter. It's still a great and easy way of building. There you can see there, so all the walls and floors made of CLT, goes together very easily. So wood, it's about speed, not just the speed of the CLT going up or the wood structure, but the speed of the follow-on trades. It's so easy to screw into wood to fix your services rather than fixing into concrete. It's really a lot in the UK, a lot of schools, universities have been expanding with wooden buildings because you can do it really quietly while all the lectures are still going on. It's very simple, safe operations on site. You will never find more than about six operatives actually putting the building up. I haven't yet figured out if it's the same 6 who go around from site to site. Now this was Sky Television. They came to us and they said, we want a building in 6 months. And we said, 6 months impossible. You haven't even got a design. But we said, well, if you want it really fast, wood is the answer. This is speeded up slightly, but it gives you the idea. Now this was going to be this was an office building. So we couldn't have CLT walls everywhere. We wanted something which was open plan. And so what you're seeing is a glulam frame combined with CLT floor slabs. They works very well. Now, had I shown you the whole video, you'd see the foundations going in. When the foundations were going in, there were about 30 guys working there, fixing all the reinforcement, pouring the concrete. When it came to the timber superstructure, there were just 6 people. In fact, it was Nick Milestone who's sitting over there. That was his team. A very, very quick process, very, very predictable. And in fact, after that, Sky Television said, wood is our preferred construction material. We want to build in wood rather than anything else. And in fact, for the 2 follow-on buildings, one was a gym, one was another office. It was the client actually insisting on using wood. Very, 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 very interesting. That's the view inside. Now, the point here is that, in an office or a school, obviously your acoustic requirements are much lower than in residential or hotels, so you can literally leave all the wood exposed. Obviously, that saves a lot of time and money on putting on all the finishes. Also leaves this really great working environment. So we've literally got CLT with just sort of fairly standard raised floors, and that's all we need. So you can see how that manages to get built so quickly. And if you want an open plan building with a frame, it doesn't just have to be combined with a timber frame. It could be combined with a steel frame. So there you see CLT as a replacement for a wet concrete slab on metal deck. Now, obviously, that CLT slab is pretty light. So if we think force is mass times acceleration, F equals ma. So if you haven't got very much mass, then when you jump up and down on your floor, it is going to accelerate a little bit more. So it's absolutely true that you will get a little bit more vibration with wooden floors. And so those steel beams you're looking at, they are going to be a little bit deeper than they would have been if that was a heavy concrete floor. But never mind, you've still got that advantage of fantastic speed of construction. But if you want to, for really long spans and sort of help with the vibrations, well, why not think about combining wood with concrete? It gives you a little bit more mass. So this is something which we developed for something called the Life Cycle Tower. A few of these have now been built. So the idea of that's just a 4-inch thick concrete slab. The span is about 30 feet. So most of the strength is coming out of the timber beams. So what you've got is something which is only about half the weight of an equivalent concrete slab. Really easy, in this case precast, easy to kind of crane into place, again fast construction. So really using each material to its advantage. This is very indicative, but it's really important that that we understand costs. It's really important that we have a material that competes. Wood does compete on cost, but I need to kind of explain to you how it works. So if you look at the bit at the bottom, first of all, is the sort of indicative sort of cost of a sort of reinforced concrete building, just the bare structure. Now you can see the cost of the bare wooden structure tends to be a little bit more. It varies on the construction type, but in Europe we're looking at 5, 10, 20, 30% more. Of course, you save on the foundations, you save on the time and cost of finishes. Typically, we're looking at 30% shorter schedules for the total time on site. There's a massive saving in that. Now, if you add all of that together, what we're finding is, really right across Europe, is that the total cost of a wooden building is pretty much matching the total cost of a steel or concrete building. Right? So that's good news for clients, because no one wants to pay more. But of course, remember, your building is now finished 30% sooner, so the client can start getting their rental income much more quickly, get more rental income. And also there's a nice sustainability badge for the building. So I think you can start to see why people are getting so excited about wooden buildings. Now, I thought I'd just finish by asking the question, how tall could we build with timber? We set ourselves a challenge. We wanted to build the tallest all-wooden building in the world. This is 19 stories. It's going up in Amsterdam next year. Now, you can see what we wanted to do. We wanted to really free up the facades. We didn't want sort of solid wooden walls around the building. So we wanted fully glazed facades. And the second thing we wanted flexible spaces. If you look at the very early CLT buildings like Stadthaus, there's lots of CLT walls everywhere. And I very much believe that even if we're building in a sustainable material, it's still really important that we build our buildings to last. And the way we make our buildings last is by making them flexible internally. So we don't have CLT walls everywhere. We just have CLT walls on the party wall lines between the apartments. And then all the internal walls are cheap light frame wood, which you can move around. Now, of course, on a tall building, what really governs the structure of a tall building is that vibration. You know, it needs to be comfortable enough for the people inside. So if you're going to stiffen up the building for vibration, then you need lots of nice long walls. So again, we use these long walls, these party walls between the apartments as the shear walls of the building. And as I say, the other thing that gives you is it frees up the facade, so those can be fully glazed, because that's what people want. Now, to make the walls as stiff as possible, you will know that in lower-rise CLT construction, you do it as platform frame, so wall, floor, wall, floor. But obviously, those kind of floors, you know, the wood's going to squash a bit, so it's going to reduce the stiffness of those walls. So what we do is, if we want to go up to 19 floors, well, we don't do that. We actually basically sit one wall panel directly on the wall panel below. You can see there's a little bit of concrete between the two, but basically, we're not squashing the floor in between. Now, we tried really hard on this. You know, 19 stories, stabilising it out of wood was quite a challenge. Why is it a challenge? Well, first of all, so if you think about a sheet of CLT, it's, you know, CLT is a really clever material, but I can tell you on an engineering scale, you know, there is a good reason why universities across the world have been spending years researching this, because, you know, you think about how that works. You try and distort that CLT panel in plane. You know, engineers amongst you will realize it's a little bit like a little sort of multi-story sort of Virendale. You know, it's pretty complex things going on there. And now, you know, if you try and make a big shear wall out of CLT, you know, this is very different from a concrete shear wall, which is one bit all in situ, all sort of joined together. You know, you've got lots of small bits of CLT, all pre-made in the factory, with joints between them, and those joints are never that stiff. And of course, then you've got door openings, and you try and, you know, very difficult to couple your walls stiffly around door openings. And so, you know, the result of that is that, you know, a CLT shear wall, it's fine for lower-rise buildings, but there's a point at which it's just not stiff enough. And so, you know, and I have no embarrassment in this, because we knew this would probably happen, but we have incorporated a concrete core. So the CLT walls, they take all the gravity, all the loads down the building, so they carry all the weight. They also take that sort of torsion as you get sort of eccentric wind load on the building. But for the main sort of wind loading, that's taken by the concrete core. And you know, have a look at Fastenep's Brock Commons. That's 18 stories, so very similar height. You know, again, it's got a concrete core, and I you know, call it a hybrid structure. I don't have a problem with that. It's just nice that we've incorporated a bit more wood into the buildings. Now, the Norwegians have managed to do a tiny bit better, because there they are architecturally, they are prepared to put the wooden structure in the facade. So they're prepared to have these big cross braces in the facade. So you've now got a much deeper walls around your building. So they've managed to go up, well, currently, they're actually going up to 18 stories at the moment. So it's not going to work architecturally for many buildings, but you can just about do it. So this is my kind of summary of that. So yeah, you know, CLT shear walls are great, really easy to build. They're not so stiff, so you're going to be looking at a span to height of something like 1 to 3 or so for those sort of CLT shear wall cantilevers. So if you're doing, say, an open plan office building, so you can have some CLT shear walls inside that. You're not going to want those walls to be too long, because they're going to break up the open plan nature. So about 6 to 8 stories is about, to get enough stiffness, is about right for those open plan timber offices. Now, if you go for something like Stadthaus or the framework building here in Portland, you know, obviously it's residential, so you do naturally have a lot more walls. And so sticking within my sort of 1 to 3 criterion, you know, you can go up to about 10 or 12 stories or so, and that's still sort of strong and stiff enough. And as I say, if you're prepared to do what the Norwegians do and have some external bracing, you can get up to maybe 14 or 16. I mean, the Norwegians have managed 18 on their current one. These are not absolute numbers. They're just to give you a very rough feel. You know, and if you want to go much above that 14 to 16 height, nothing wrong with incorporating a concrete core. Now, we shouldn't just talk about stiffness and vibration and strength. You know, there are obviously other things which affect height. Dave Barber spoke yesterday about fire, you know, the fact that wood chars very nicely, so that charred layer insulates the wood behind. But obviously, you know, if you start doing bigger buildings in wood, you need to think about that extra fuel load that you put into the fire, and you need to make sure that your structure survives the fire, because there's still going to be people stuck high up the building if you're doing a bigger structure. So, you know, the wood works fine. It simply means that for bigger, taller structures, you're going to start progressively covering over more and more of your wood structure. But as I say, it still makes a really good structure hidden behind the fire protection. And the final thing, of course, is gravity. You know, obviously, as you go tall, you've got more load on your columns, and those columns are going to get bigger. And there's going to come a point at which the client is going to say, well, you know, if I start having these big wooden columns, that's going to take up my lettable area, and I'd rather, can we make them smaller? You know, can we make them steel or something like this? Now, obviously, you know, Brock Commons has got columns at sort of 10-foot centres, and so that's kind of fine. But you know, you can imagine that's pretty much going to be the limit, and you're going to imagine generally people are going to want a lot less columns. So this finally is my prediction for the future, really, in terms of what we will be building in 10 years' time. You know, as Jeff said, at the moment we're very much in this research phase. You know, you can build all sorts of things in wood, and that's great, but the question for me is, where is it sensible structurally? Where can it compete economically? Because that's the long-term story. And I think there are 3 areas where we will be using wood. So the first one is low-rise buildings, let's say up to about 8 stories. So up to about 8 stories, so that's fine from a fire point of view. We can expose all the wood. If it's all exposed, you know, so the acoustically, it's you know, that's going to work fine for things like schools and offices. So I think schools and offices up to about 8 stories, complete wooden structures. So the next one, the residential hotels, student accommodation, all that kind of thing. You know, obviously here you need really good acoustic separation between all the rooms. And so there you're really going to be wanting to cover over all your wood or most of your wood for acoustics. You also want to cover over most of it for fire. I think that's what they call now this new type 4B over here. So about in that sort of range, 5 to 12 stories. Remember, 12 is my sort of upper limit for what we can roughly stabilize with CRT shear walls. I've said 5 to 12 because, you know, below 5 stories, it's going to be light frame timber. There's nothing, that sort of balloon frame, nothing can compete with the cost of balloon frame type construction at those lower levels. But once we get above the limits of what that can cope with, then that's where your sort of CLT massive timber construction kicks in. You know, and then above that, no reason why you can't go above 12 stories. 2 provisos. You know, first of all, you're going to need a concrete core to make the building stiff enough. And you know, at roughly that sort of height, you're going to start needing to cover over most or all of your wood to really stop it engaging in the fire. So I will come back in 10 years' time and see if I'm right.